cloud. Chat window. All right, let's restart. Okay, what just happened? We were recording on QuickTime and Discord, but it didn't work out, so we're just gonna restart. So welcome to ACM AI Reading Group. This is our first meeting. Today, checking code is AI papers, but if you're watching recording, you can't use it anymore, unfortunately. So today's paper is enhancing the reliability of out distribution data on out distribution image detection in neural networks. That's the paper, that's the code. Make sure you can also follow the slides on the link provided in the Discord channel. It'll also be shown at the end of the slides. Keyword, out distribution data. It refers to data that is not part of the intended distribution and models trained on. For example, pictures of cars are not in the same distribution of pictures of cats. Analytical data on oil is not the same distribution as data on housing prices, just as examples. Let me close Discord. So neural networks, for the purpose of this paper, you don't even really know what they are. Just think of them as a function, a multidimensional function, multivariate function, taking some vector x as input and returning the values f1 of x plus f2 of x plus f1 of x, comma, f2 of x, comma, f3 of x, so and so to fn of x. And what a neural network does when you add the final layer is that it predicts a label, a classification. So if, let's say we're taking an image of cats, we want to classify it as, okay, let's just say cars. We want to classify as a Honda, a BMW, or an, I can't think of Ford, okay? So there's three classifications. What we do is the label we predict is argmax of f of x, which basically means Tesla, yeah, okay. Argmax is a function you guys might have heard of, very commonly used in NumPy and all that. Returns the index of the maximum value of an array. So f of x returns you an array of n values. We take the index of the highest value in that array. That's the label we classify it as. If you have any questions, feel free to stop me and ask, or just put it in the Discord channel or in the Zoom chat. Softmax scores, this is another common thing that's referred to a lot. Softmax is the activation function applied in the final. Make sure to mute yourselves, y'all. Okay. Yeah. Softmax is an activation function applied in the final layer of neural networks to map values from a neural network to prediction probabilities. They're also known as confidence scores. Whichever neuron outputs the highest softmax score is considered then the final predicted label. And again, we go back to the argmax argument. Next slide. So here's a problem statement. Looks very complicated, but basically given a sample space, an image space, chi, or you can just call it x, this little squiggly symbol I think is called chi, which is composed of two subsets, p of x and q of x, where p of x refers to in distribution images and q of x refers to out of distribution images. The question now is, can we distinguish, given an image x sample from a mixture distribution, can we distinguish which distribution is the image a part of? Is it part of p of x or q of x, in or out? Wait, let me open notes. I wrote notes down here, but I forgot. Where are these notes? There we go. Next slide. So here are the key main ideas of the paper. If you read it or if you didn't read it and you didn't quite get what happened, the idea is it's based on previous research where people have observed that when using a softmax layer to output confidence values, typically for in-distribution data, outputs higher probabilities than out-of-distribution data. I'll show you guys a graph of this later. ODIN, which is the term for this framework or this idea of, I forgot what it stands for. It stands for out-of-distribution data detector in neural networks. It's a weird acronym. Goes one step further, instead of just looking at higher probabilities via lower probabilities by utilizing more information from our neural network. Remember our neural network F returns data F1 to Fn. Softmax kind of just uses that data and that's it. ODIN plans to use two techniques, namely temperature scaling and input preprocessing to small perturbations to use that data to its full value and kind of just add it to that softmax layer. ODIN, what's really special is that it's simple to add to any pre-trained neural network. ODIN lets us build an out-of-distribution data detector as a first step before using the final neural network prediction, which as we recall is basically argmax. That's the prediction a neural network makes. So here's what I mean by a softmax score. So PI here stands for the softmax score of the ith data point. Yeah, thank you for answering the questions. And if you look at the graph below, this is what previous research has done, is that they've shown that the distribution of scores overlaps. So for in-distribution data, the green line here, you'll see that it has a huge, you'll see that it's typically higher than out-distributed data. So you can see like the center of the distribution, like the mean or mode, or median, whichever one you want to use. Probably use median because this is skewed left. It's higher than out-distributed data. So this is a really crude metric to determine is it in distribution or out distribution. So let's just say we're just using the median difference. You see that the median here is here, but if the median of the green distribution, the in distribution data is really up high, we have all this data to the right, right? In the out distribution data that will easily become false positives where we think it's in distribution and continue to predict on it, whereas it's actually out distribution. So this entire overlap of these two distributions gives us a decent metric, and this is what they talk on paper. It's like a metric for how badly you will misclassify things. As an example, in this traffic sign data set, you see these confidence scores are typically higher, but for these other images that are in out distribution, cars, oranges, plants, mailboxes, they also give you high confidence scores. But it's hard to differentiate it. Like at what threshold are we gonna have it? What slide is this? Okay, Edward, I'll let you explain that. So here is what happens when we do something called temperature scaling. In particular, you see this function up here. For this function up here, if you set t equal to 1, this is actually the softmax equation. But when we do temperature scaling, where we take all our outputs from a neural network's predictions, scale them down by a factor of t, we see that we shift our distributions to the left. And you'll notice that the overlap of these two distributions, out distribution and in distribution, becomes significantly smaller. As a result, this makes it such that we can more reliably determine whether or not the data we're given is out distribution or in distribution first, then proceed to make a prediction. Anyone have any questions or concerns? You can speak up or type in the chat. What's the threshold for this? We don't add, so the threshold we'll talk about a little later. What the authors do is actually they pick a threshold that guarantees a TPR, a true positive rate of 95%. We'll get to that a little bit later. But you can see that if we choose a threshold just using temperature scaling only, we can already have a massive improvement. This is just a visual idea. Just a further analysis in the paper that's really mathy that we probably won't get. We will get to a little bit. Any questions? All right, I'm gonna move. We move. So here's the intuition. Oh, could you go over to temperature scaling one more time briefly? All right, I'll go back. So temperature scaling, all you do is remember our neural network F returns n values, an n-dimensional vector, column vector. And each of those values is equal to f of 1 of x, f of 2 of x, f of 3 of x, and so forth. So you see f of I of x, fj of x represents those n values. What we do with temperature scaling is before we apply softmax, we first scale all those prediction outputs down by a factor of t, the temperature. And then after that, then we apply our softmax function, which is basically taking the exponential of each of the outputs, take the exponential of one of the outputs, summing over all the outputs, exponentialized. Does that answer your question or anything else that's confusing? All right, here's the intuition. This is very complicated looking, but this is this is directly from the paper. Here, this is actually the same equation as this, but what we do, what the authors do is they do something called Taylor expansion. If you haven't taken multivariable calculus, or I think they teach it in single variable, Taylor expansion is basically an approximation at some center of functions. So for example, the Taylor expansion for exponential functions is well known, and it actually gives you this. So I'm not going to go ahead and explain the derivation. The derivation is actually in the paper. I should pull up the paper. Give me a second. You can check the appendix B here for derivation for the Taylor expansion. Where is it? Yeah, here we go. Yeah, so it's just this. You'll see the Taylor expansion is just basically a sum of these values or like differences, right? Over a constant squared, constant cubed, and so forth, and then plus some lower order terms. I'm not gonna explain this too much. The main reason, based on this analysis using Taylor expansion, we actually get a good intuition about why it works. So what's also observed for typically out of distribution data is that out of distribution data is less confident between predictions. So we call that neural networks makes n predictions effectively. They make n confidence value scores, referring to how confident they are is one of each class, one of those n classes. What happens is that our distribution data typically has more similar values between each of the n confidence scores, whereas in distribution data typically has more stark contrast. So for example, let's say we have three classes, Hondas, Fords, and Teslas. We're trying to predict if this car is a Tesla. Let's say we're given a car that is actually a Tesla. More often than not, the confidence score for Tesla classification will be very high, let's say like 0.99. And the confidence scores for the other two types of cars, Hondas and Fords, will be very low, like 0.1. But if we're given out distribution data, let's say a mailbox, what might happen more often than not is that, let's say for the Tesla confidence score, it's pretty high still, 0.9. But the other two scores are also pretty high, maybe like 0.5 and 0.8. So what we're doing here, if you look at the bottom numerator term, we have f y hat of x minus f I of x. Y hat represents the predicted label. So what we're doing is we're taking our largest output value, remember argmax, largest output value from our neural network and subtract it pairwise from each of the remaining outputs. And what you will see is that typically out distributed data will make this summation here much smaller. Does this make sense to anyone? Or is anyone not following? All right, so this is the intuition. By making it much smaller, we're kind of effectively adding a metric using this information to encourage our network or our out distribution in distribution data discriminator to throw out data that is not confident in itself and it doesn't have a high enough contrast between pairs of values. Okay. Yeah, and if data were in distribution, the network would typically be more confident and have clearer separation of classes. All right, what's the next thing? Edward?
Wait, you can start explaining it and I'll just like add on like after.
Okay, I'll explain what part are you gonna add on?
So in your slides, there's like a question about how I don't understand that this well. Well, I'm just gonna explain that what the X with the curly thing on top is just for input preprocessing, which basically just adds essentially random noise into the input. Yeah, that's basically it.
Perturbations, this is also a common thing. This is just adding noise, a little bit of noise with some magnitude epsilon. If you don't know what an epsilon symbol is, it's this little e that's curled. What it effectively does is first we take the softmax scores, the original softmax scores, with the temperature scaling, take the gradient with respect to some input x, get the sign, multiply by this magnitude epsilon, and that returns x tilde, which is our pre-processed sample or input x. Then we do the same, we pass x tilde through again, and that gives us the new part. So there's two steps. I'll explain the steps of the algorithm or the Odin later. But first, just to understand that this, typically what it does, as observed by the researchers, is that by adding these perturbations, more often than not, in distribution data will increase in confidence scores much more than out distribution data. So you'll see that these distributions both shift up, but in distribution data shifts up much more. And Edward, do you want to explain anything else?
I think you did a pretty good job. You're chilling.
Okay. Yeah, and also for those who might not know this, because is it like an optimal t-value? I'll get to that soon. The paper has a section about hyperparameter optimization, and they explain how they choose the parameters. Just a quick touch on notation. Log, you guys should know what log is, logarithm. This upside down delta symbol, this is gradient with respect to x. This is a typical symbol used in multivariable calculus, and the reason why we use this symbol to find a gradient instead of just one-dimensional derivatives is because x is an input vector. It's a vector, not just a single dimensional vector. Wait, so you said before the softmax is just when t equals 1. Yeah. Here, I'll find the Wikipedia article on softmax. This gives you the equation. And you'll see that the same thing. So softmax is this. You take the exponential of all the inputs. Oh, sorry, this thing here, all the inputs. And what we're doing instead, or what the researchers are doing instead, is they're scaling it down by t. So if t equals 1, it's the same thing as this function here. Does that make sense? All right, I'm going to go forward. Are they finding a better softmax? They call it a calibrated softmax. I wouldn't say it's better, but it's calibrated to be to cause this kind of situation to happen. It's the preprocessing is for any data. So I'll explain the steps, and this will be more clear. If you go to the slides, they describe their detector, the out distribution data detector, and it's effectively building a decision boundary between in distribution data and out distribution data. And after I explain this, we can go to discussion. So what we effectively do is first define a pre-trained network F that classifies n classes of images. For any input x, feed it forward through the network F and calculate the confidence of each of the n classes. After that, calculate the perturbation needed using the input processing method on x. So if you recall this, we first find p y hat of x, and then we apply this into this equation, get x tilde. We add perturbations to x to produce x tilde, and then feed x tilde through the network F again. After that, we apply temperature scaling to the output of network F on x prime, calculate the confidence intervals again, confidence scores again. And now here's the step where we do the threshold. If the confidence value is calculated after using our calibrated softmax, where we calculate this confidence, if the value is above some delta, mark as in distribution and use predictions. Otherwise, flag as out of distribution and don't use the predictions. Any questions about that? Let's have this. No. All right. So the way someone asked a good question: how do we choose t? How do we choose epsilon? How do we choose these hyperparameters? If you look at this paper, they talk a little bit about it. Effectively, they chose where is the hyperparameter section? So they have a separate OOD validation set. For temperature, they selected all these different values, and for different magnitude, they chose 21 evenly spaced numbers from 0 and ending at 0.004. The optimal parameters are chosen to minimize the FPR at TPR 95% of the validation OOD dataset. Yeah, so if you don't know what FPR and TPR is, this is what it is. FPR is a false positive rate. Sorry, yeah. It is a percent of out distribution data incorrectly classified as in distribution. TPR is a true positive rate, percent of in distribution data correctly classified as in distribution. So the researcher's goal was to maintain TPR of 95%, so high classification accuracy, high precision, or what they call, I think, specificity, and then make sure that the number of false positives is minimal. Edward describes it well. We want to keep TPR 95% and choose T, epsilon, and delta such that FPR is as low as possible. Any other questions? Yeah, Sayam Gupta, you bring up a really good point. They do talk about what happens when you have large T. In particular, when you have large T, the Taylor expansion becomes a lot worse in the fact that it becomes harder and harder to compute. Does this have to be recalibrated for each training, or can the same parameters be used for all applications? It depends on the network. So you got to choose it, I think, depending on the network. They do have a section talking about parameter transferability, which we can talk about later in discussion. But the idea is that this doesn't affect the network at all. It's added before the network. All right, and yeah, this is the results. They reduced the FPR from 34.7% of previous research to 4.3%. All right, now it's the discussion. These are just some discussion questions we put up here, but you guys can also bring up your own. And I encourage you guys just to answer however way you want to answer it. Yeah, I guess first question is this robust? So a topic I think the researchers bring up, I don't know if they bring up in the paper, but they brought up in the seminar, is that given small perturbations to out distribution data, will it still be able to classify it as out distribution? So I think the question was, someone asked was how volatile it is. Okay, Edward raised his hand.
Yes. Oh, wait, wait. It was like a follow-up question to how robust it was. So I'll just wait until you answer that question.
Okay, wait, I can't really answer is this robust. This is just a discussion. Like, do you guys think this is robust in the terms that, let's say we feed it an out of distribution image, like a mailbox. Let's say we change the mailbox just a little bit. Is this a problem? Is this not a problem? You guys have any thoughts?
Wait. Are you able to hear me?
Yeah, I can hear you.
All right. Yeah, I want to say this is robust because they like talked about how you can retrain the data or like the network again after you get like enough perturbations or like enough things that don't really agree, or there are like enough. You can basically create another class of out of distribution data sets or like out of distribution things and like make them in distribution. I don't know, something like that. But I would want to say like this could be made in robust like applications. Probably it has a pretty good like feature of classifying things, and if like it can do that thing better on for like more data, then I think that should be possible.
Yeah, that sounds like solid points. Any other thoughts? Or Edward, do you want to just go now?
Yeah. So I had like a more of like a general question about this paper, because how it's training, I guess it's like more of like a overall, like why this works kind of question. Because what Odin's doing is that it's essentially just, well, I would say adding noise to the input data. And as a result, how I see it is that the input images are just like messed up to a certain extent, such that it's going to think that it's either an input, it's either going to be in the in distribution or out distribution. So I guess my question is how this actually extrapolates to unseen data, like because in the video it shows how if it's shown different types of signs, it can somehow extrapolate to like cars and stuff like that. So my question is how it's able to do or like link those two.
Yeah, that's a good point. I think this is also a little bit related to the third point on the discussion I put up earlier, which is when they tested Odin in that paper, I think they only tested against uniform and Gaussian generated data as out distribution. Now the question is this a reliable test measure? And Edward's argument is kind of just asking the same similar question is, they tested against these uniform Gaussian generated data, but how about other data that might try to trick the Odin detector? I personally think it's not that good. And this kind of goes back to robustness in the fact that it's not too robust against out distribution data, mostly because the paper doesn't indicate anything about extrapolation, as Edward brings up. At least this is in the paper. Maybe I read it, I didn't read it hard enough, but if you look at their table or their experimentation, let me look for it. Yeah, so this is their out distribution data sets. They do test against tiny ImageNet, LSUN, and Gaussian noise and uniform noise, but these are very specific data sets, and it's really hard to, let's say, cover all possible different classes. So like, or different patterns. It's like a tiny ImageNet has 200 different classes. LSUN has like, I think 10 classes, not that many. And they're fairly small test sets, I think, compared to some like the state-of-the-art ones. I would say that the real world, in a production environment, you can feed it a million different classes, which makes this a little bit more difficult. Someone just asked, I think the validation set used for hyperparameters is only one set as well. I do not recall. I don't know what they wrote. Yeah, it's a little bit limited. I mean, this is a really good start, I think. And I think they've done, this is like 2 years ago. They've done like a lot of further research into this. In fact, robustness was something they talked about a lot during the seminar. They presented parts of this paper. Yeah, they have a separate OOD validation data set. How do you know you've actually done it for all possible out-of-district data, especially for certain edge cases that might be iffy? Yeah, so like, that's a really hard question. Can you show out-of-distributed detector function? Yeah, let me go find the function they wrote. They just call it G of X delta T epsilon. Here we go. This P here is the calibrated softmax. X tilde is the pre-processed image sample.
Wait, I want to add on to Joseph's point, but like I cannot type that much. So like what he's saying, like all possible out of distribution data. I think like in the seminar she mentioned that out of distribution data could be infinite. So like they cannot really like train it for all the out of distribution data. So what they want to do is basically make a detector that could reduce the false positive rate, which I think it's pretty well, and like it would be able to do that. So
Yeah.
like even if you are running on a like on the cars, so it doesn't matter if it's a mailbox or like a traffic sign, it would still say that it's out of distribution.
Yep. That's a good point. The paper is successful within the scope it's shown. But again, we have to yeah, I don't know actually what other comments to talk about this. Any other thoughts about generalizability? Any other questions as well? All right.
Wait, I have a question.
Yeah.
How exactly did they determine the so I think in the paper there was a section where they were describing like the perturbations. Wait, let me find that. Yeah, it's like in input processing. How did,
What is it?
like, what exactly does that do? I'm guessing like it's inspired by the adversarial paper that they're talking about, but
I believe
like, why is it good for them to increase the softmax score of like any given input?
okay, I think I wrote my notes, but I don't think they actually explained the math behind it. They just said they observed that. They say a salient observation is that CFAR10 images, you know what CFAR10 is, just a giant data set of images, which is in distributions, tend to have a larger values on a norm of gradient than most out distribution images. They say this is an observation. I don't think they actually explain more closely why this is actually working. No, I personally don't know. I actually personally think these perturbations might be very dependent on the data set you choose. Or maybe just how, I don't know. Let me try to read this again. I don't think they talk about this very in depth because they purely say it's just an observation that this is true. This is just demonstrating effects in an image. It illustrates the effects of the norm of the gradient, which is the perturbation here, down here. Suppose as an individual, blah, blah. Yeah, they don't explain this that well. They do refer to research from before where small perturbations actually does cause, tends to show that softmax scores tend to change significantly if small perturbations are added to indistributed images. But again, they don't actually have good reasoning for this or even good intuition, honestly. They kind of just say, oh, we observed this, and that's it.
I could give my take on why I think it's true.
All right.
So in the equation, like for, actually, can you go up to like, it's like at the top of page 3.
Page 3, all right.
Yeah, right there. Wait, higher up. Oh wait, sorry, page 3, yeah. Yeah, so for the, equation 2, basically it's only looking at the sign of the negative gradient, right? But since we're subtracting it, it's basically adding like the sign of the gradient, right? So basically what it's doing is it's going in the like direction that's going to be proportional to like, how to say, like if we know like this input X is going to greatly increase our softmax score, right? Then we basically want to follow that direction. Like we want to increase it even more, right? So it's basically proportional to like what's happening with our softmax conditioned on the input, right? And so what I think it's doing is like, if you imagine like, actually on the slides, you have like that line, and then you have like those distributions. Basically what I think is happening is that it's encouraging the distribution to shift upwards or downwards, depending on like the sign of the gradient. And I think that is just to like help like separate the, like the in distribution versus the out of distribution curves.
I see. Yeah, that's pretty clear. For small perturbation, oh, okay, they do explain this a little better here, actually. And Jason's right about this. Small perturbations are added, epsilon, to decrease the softmax score for a true label and force the neural network to be wrong. This is the idea of using adversarial examples. Here, however, our goal setting is different. We're trying to increase the softmax score using the negative gradient and the sign. Yeah, without the need for a class label at all. I still think this doesn't explain well why. It doesn't explain why out of distribution images tend to increase much less. Unless maybe the Goodfellow article explains that. I don't know. It's not that confident. I mean, we can easily talk about the implications at least. If we see that out distribution data tends to increase much less, it's basically showing that maybe is another way of saying that out of distribution data is less confident according to the neural network. Because let's say if you're a person, right? If you're confident this direction will increase your confidence a lot more, you're obviously going to take it, right? But if you're less confident about which direction to go to, meaning lower softmax scores and lower smaller change or smaller gradients, or gradients in the wrong direction, you probably wouldn't use it. Maybe that's not, I don't know. Okay, someone asked, I think the rationale for it is they can use a noise to increase the difference between in and out distribution data. Yeah, so that was observed. And they used this past article to explain their intuition, but as a pure mathematical reason why, I have no idea. The closest explanation I can think of is gradients, and just deciding to go in the direction of gradients that are bigger and going up. Like, I think maybe this image helps a little bit to explain why. They do a 3D mapping here. So you'll see this. For a point like SX1, you see that the gradient with respect to the input is very, very big, right? So clearly you want this example, which is already a little bit on the edge, right? With a low softmax score of about 0.5 to be much higher. And we increase it to 0.999 or something. But you'll see for softer examples that are out of distribution, it may be as a coincidence that for out of distribution data, the gradients around that data point tend to be much smaller. And as a result, won't change as much because you're less confident. Any thoughts? My explanation is probably waffle. Like, it probably might not be right. I encourage you guys to bring up other explanations based on equations or anything. Oh, Edward likes it. Which part of the code is temperature scaling? Wait, Catherine, did you add this question or did someone ask this and I didn't answer it?
Oh, I asked this question.
Oh, wait. It's like, it should be in the slides. If you go to slides, I added links for all the code on like the exact part. So let's say temperature scaling. Also, their code is really badly written. Like they copy and pasted their code for each of their different tests. It doesn't make sense. So here's temperature scaling. They literally just scale it down by a /temper. It's really simple. So what you first do is you feed it through the network, right? And then you divide all the inputs. And this makes sense. If you're a little confused about the math, go back to the equation. Simple as the number of the neural network outputs is f of I, right? F of j. Just scale all of them down by t first and then apply softmax. And you'll see that softmax is applied here. Okay, maybe let's move on to the next question. I think this is talking more about implications and stuff. Oh, this is the second question. If you haven't gotten here. How do you guys think this can be applied to data other than images? Thoughts? Because this research paper focuses on the domain of images, but do you think this can be easily extended to other data? Or is this just something special about images that make it easier to apply Odin or not? What's this down?
Shazam, like it detects the song that's playing.
Oh, that app. Yep, I guess. So I guess if you're seeing really badly, it'll just say it's not music. Audio data, particular architecture. Okay, here's a powerful thought. Something important about image data is, remember that when we have an image input like X, right? It's composed of if you guys don't know, typically they are RGB values or grayscale values at each pixel, all condensed into one matrix, so one long vector. Something special, especially when applying convolutional layers, is that these 2D matrices representing images have locality, which not all data has. Locality just basically means adjacent pixels are related to each other. Like adjacent features are related to each other in some form. And if you don't know, convolutional layers is applying something called convolutions, which takes advantage of this locality feature of pictures. Like for example, locally, your face should be together. But for other kinds of data, it's all spread out. So let's say we're looking at like audio data. I think this might also work for, yeah. I think this will also work for audio data because audio data also has some form of context and locality in the sense that the audio at timestamp t and timestamp like adjacent to like t plus epsilon for small epsilon, it's gonna be very similar. It shouldn't be jumping too much. Someone also mentioned, what was that other way? Yeah, so you don't think so because it doesn't depend on a particular architecture, which is true. Based on their research, they can apply Odin to any classification as long as you're using a neural network, because this only works for neural networks, I think. But the idea can probably be applied to other areas. But the issue I have with this is that suppose you have like Boston pricing data. Your different features form a feature vector, but there's no locality at all. What's shift invariant? Oh, it doesn't matter if the CAS on the left or the right side of the image is still detects tab. Oh, okay, shift invariant. They fix what? Wait, Tristan, can you elaborate? Truly shift invariant. Yeah. Any other thoughts about locality, shift invariance? Does someone want to explain what shift invariance is? I don't think everyone will know what that is. Catherine?
Oh,
or does
yeah.
someone explain shift invariance?
Yeah, so shift invariance is basically when like, so if you have a picture of a tiger, even when it's on, I mean, I'm sorry for butchering your name, basically described it. Even if it's on the left or right, it still gets the correct prediction.
Oh, okay. Nice. Any
But I
other
don't know.
thoughts?
Like I was in a separate reading group and we had a huge discussion on why like CNNs aren't like actually completely shift invariant, which is what the paper I linked like discussed.
Mhm.
So basically there's still a difference. Like ideally, if CNNs were truly shift invariant, it would mean that there isn't like an accuracy difference between, you know, images where cats, if you're trying to identify a cat, like whether it's on the left or right, there shouldn't be an accuracy difference, but there is, which is why I guess CNNs aren't completely shift invariant. But it's been a while since I read this paper, so.
It would have to do with like direction in some way. Like the locality we're measuring with like convolutional layers, measure locality in one direction, or like I guess space. I have no idea. I think that applies to inverted and flipped images as well. I feel like it should. That's kind of shift, right? What I think one way people will try to address this is that um, they use data augmentation. So this is a really common thing you might see in like image classification competitions and like tutorials. It's like they always take your given data set, apply rotations to all the images, apply flips to all the images if it makes sense, and apply like shifts in X and Y directions of the image. This is to create more data, but I think this also might help address the shift invariance issue. Kunal just asked a question, what's an example of data which doesn't have locality? Example is just Boston housing prices. For example, in one of those typical Boston housing data sets, they include data such as number of bedrooms, front yard area, area of the house, number of floors, number of bathrooms, age of the house, when it was built, price, right? These are all clumped into one feature vector adjacent. So like the first value might be the price, second value might be the year it was built, next value might be the number of floors. Obviously the year it was built and the number of floors probably has very minimal correlation. And there's not much locality, like they don't relate to each other that much. The only correlation you can think of is maybe that as the years go on, floors get higher, but that's really hard to say. And then if something that really doesn't make sense, like so say the number of floors it has and, okay, the locality is just minimum. I can't think of an example where there's no locality. Yeah, but does that make sense? For why, if you took like these random values that are for the same data set, but don't relate to each other as much, they have a low correlation. Locality between features, sorry, not the price. The price is the label. Or like, yeah. Locality between the features. So like, let's say the location, house, and number of floors. So there's probably very little locality. You can argue that maybe if you're in a location that's like city center, the floors is probably gonna be higher. If you're in the suburbs, it might be lower. But again, this depends on the data set, exactly. This is why for like those data sets, you kind of just do like linear regression or something, and then it's fine. Any other thoughts about extrapolation? You think it would be pretty hard to apply this to other things other than images? Fourth point. Yeah, we'll talk about the fourth point. I actually disagree. I think someone brought up audio data, and I think it could be applied to audio data as well. Because now I think audio data has the same feature locality, which I think is crucial for CNNs, convolutional neural networks. And to a certain extent, Odin kind of requires it to be some form of locality, I think. Okay, we're running out of time. We probably have like another 10, 15 minutes. Let's try to move on to the next point. Next point. This is like kind of a random question, but it's related to allo distributions, is what might happen if we instead had n+1 classes with the n+1 class representing allo distribution? Is this feasible? Is this possible? What are your thoughts?
Oh, wait. So towards the end, when she was like talking about the real world applications of this thing, she talked about like a real world model would be that you get input from the user, and if it is like out of distribution, you retrain your data, and if it is in distribution, you just like add this to your neural network as this, like another example of a class that you already have in the data. So I thought that might be somewhat like of this point, because like if you get enough auto distribution points which are kind of like similar in something, you can like create another class with those data points.
But my only issue with those other data points, like you can have like separate class of other, right? And train your neural network as normal. I think one possible issue is that other data is very scattered.
True.
So let's take like a Gaussian distribution, or just simple uniform noise. It's very scattered, and some of the data points are actually really similar to the actual in distribution data. I mean, that's like just FPR, like that's gonna happen. I don't know. My only issue with registering things as other is that typically we've always seen like neural networks classify one class of similarly patterned images. I think it might not work as well, right? Since the perturbations wouldn't have the same effect if the confidence in the out distribution data increased as well due to the perturbations. Okay, this point is actually kind of like out of Odin. We're just kind of talking about general neural networks and adding the n+1 class. So instead of using temperature scaling and perturbations to determine out distribution or distribution first, instead we'll just have a neural network of n+1 classes, and it will give you a confidence value of each of the classes. And if the highest one is the n+1 one, we throw the data out. If it's not, then we predict it as in distribution.
I was thinking about this too, like when I read the paper, and I think there's probably arguments for both sides. Like in one case, it might be a case that if you try to train this n+1 class that tries to catch everything else, then there might be like too much variance in the data that falls under this class, and you'd probably get really poor performance on like actually classifying this as out of distribution. But on the other hand, like I think if you think of this as like drawing decision boundaries in like the input space, then it could be that like you draw these boundaries for all of these first n classes, but then everything outside of those boundaries is in the n+1 class. But I don't know which like case would actually happen.
It's hard. Like just think of a, I don't know, like just think of a 2D. So let's say we have two features, right? Like X and Y. And we have like n classes, like clusters. If the clusters are like everywhere, right? Let me see if I can get a good image. Oh, wait. I need to figure out where was the website that had clustering. It was random clustered data. My issue with that is that the decision boundary is very complicated. Let me just try to find something that's really, that's full of lots of complicated things. Here, let's take this one, for example. No, it's not a good example. I'm trying to find a good one. Spaced out. Okay, let's take this one, for example. If we have like these three clusters, these three classes, right? And let's say everything in between them, all this gray space out here, this gray pinkish space is out of distribution, right? The decision boundary we're trying to change is very complicated in the sense that you're kind of like making weird loops, right? And this is just a 2D space. So obviously if we had more features, it'd be a little bit easier to model. But we're not always gonna have that. We're not always gonna have like good features all the time. So like in a lower dimensional setting, this could be really complicated to make a decision boundary out of.
I think like one more point that you can make that why it might not be possible is that you can have like any point out of distribution. Like she said that there are infinite out of distribution data points. So like if you have infinite data, You can like literally make any data point, and that's supposed to be n+1 class. So I don't know how you would like train your neural network to accommodate for that.
Wait, can you repeat the middle part? I might have missed it.
It's basically like you don't have enough data for that, or
Oh,
like you cannot probably compute it because there are infinite out of distribution data points.
yeah, this is another question. Like, how do you deal with collecting the data for out of distribution things?
Yeah, exactly.
And someone else just asked this in chat. I think the risk of adding the n+1 class would be finding adequate testing data. And this is a good point. We were already talking about the training section, but the data section is also very important. Computational resource might also be worth accounting for when thinking about scalability. Yeah. I kind of explained earlier, and Jason also explained, is that even if you have a bunch of classes, but limited features, it'll be very hard to draw the decision boundary. And the more complicated the decision boundary is, the more likely it's going to take longer to train. Okay, maybe let's talk about compromise. Maybe what if we just wanted to we want to train our network on maybe cars, but make sure that pictures that are commonly associated with cars, right? Let's say roads don't get classed as cars. Does that make more sense? So using context to our advantage. So let's say we're at a company that wants to recognize different types of cars, given images of a road, right? Images of cars on a road. Would it be more feasible if we helped train classes recognizing other things, which includes roads, traffic lights, other things you typically see on a car next to a car? So that in the event that a car is not in the image for some reason, we realize it's not a car. Thoughts about that? About limiting scope? Context-specific outbound classification might work. Good. Perhaps establishing a frequency threshold for objects within the data set. Can you elaborate, Karthik? Karthik? Sorry, I don't want to say your name wrong.
You're good. I was like thinking like if you had, so I mean, I guess if you have a data set with cars on the road, for example, I guess a road is something that pops up in every single, or like it'll pop up in most images of cars. So it's probably worth training for that. But then there might be something that only pops up like 60% of the time in an image with cars, like maybe a stop sign or a crosswalk, something like that. So then if you establish a sort of like, if you take a sample of your data set, then create a threshold for different objects, like in the frequency they come up, it could work.
That's a good point. I've seen research where this was research into HCI and ML. There are these researchers analyzing different methods to reduce bias in a model, and one of the ways is to filter out your data set a bit. So what you're describing is kind of like a filtering, right? Like you're just making sure the data set only has some proportion of objects. Or did I read that wrong?
Yeah, kind of. Yeah, basically just.
Yeah.
Yeah.
In the context of bias and like discrimination and ethics and like HCI, one way people have addressed one of the really common issues is called weird, where all data sets that are using research is always white, economic, intellectual, rich, no, I forgot what D stands for or something. Basically, there's always like the same people. So there's always some kind of skewness to people falling on that one demographic of white people. So one approach to this is just editing our data set to have a more balanced, diverse set of individuals and elements. So I guess this also applies here. Maybe in the context of out of distribution data detection, we might want to consider what data to include into our data set. Do you have any, Karthik, do you have any ideas about what kind of threshold you would use, or how would you go about deciding that?
That would be a pretty tough question. Because I think it's like, where do you draw the line of too many objects to train for versus...
A better question is like, what will you consider when deciding the threshold?
I guess the impact it would have on the accuracy, I think maybe. So I don't know if it's having I guess if a certain object has a significant impact on the accuracy, then it might be worth training for that versus not. But it's kind of hard to tell whether it will have a significant impact, I guess.
Okay. All right, let's go to the last question. What implications in future work does this paper lead to? Thoughts? This is always like a question to ask every paper, I guess. It's just like, how do you generalize it? What does it imply? What can we do in the future?
I have like a point, I guess that's like that works out for most of the training things that are done. So basically, like, what if someone uses their algorithm to train another neural network that is out of distribution but ends up being classified as in distribution by this data set, by this neural network. Basically using this neural network to make a better one, you know, deep fakes and their detection goals.
Okay. But I feel like that might get into the issue of like n+1, where the n+1 class is out of distribution. It might not be feasible. But it's still a worthy point. Oh, Jason just asked everyone, does anyone have any questions about reading papers in general? Because I know not all of you guys are doing research, or not all of you guys read papers that often. So now's a good time to ask some people who do read it often, like Jason and other people here, if you want any tips or anything. Okay. I think this pretty much wraps it up. It's been like an hour. Yeah, thank you for you guys coming. We'll send out a quick survey just asking for feedback about difficulty, how interesting the paper was, and also the feedback form. You can also submit, optionally submit a paper you want to have everyone look at or review the next session. Just give us a link to a PDF or something, or a link to find it. And you can also optionally submit your interest to lead a session yourself or help develop these slides. Yeah, I'm gonna send you guys the link in the Discord channel, but other than that, that closes up for the meeting. Thank you guys. I'm gonna stop sharing now. Or stop recording. Stop.